Don't think more people will be joining. Should we just start?
Yeah, I think we should start.
Sorry?
I think we should start right now.
Okay. Sure, I'll just share my screen. We'll start with part one then.
Yeah.
Okay. Okay, hi everyone. This is the homework for bootcamp. So we'll just be covering a few introductory details about both parts. So the write-up for both parts this time is pretty long and very detailed. So a lot of details are covered there. So we'd really encourage you to go through the write-up properly from the start to the beginning to understand what all has to be done. Uh, that will actually clear a lot of your doubts. So before like jumping onto Piazza or going to office hours, please make sure to read the write-up properly. And we'll be touching on the main highlights of the write-up from here in the bootcamp. So for part one, there are two subtasks. The first subtask is self-attention. You'll be implementing self-attention's forward and backward equations. Self-attention has already been covered in the lectures. So you'll be implementing that. That is 20% of for part one. The second part, which is the bulk of for part one, is language modeling, where you will be training a language model using LSTM cells. Whose and language modeling, the task itself means to be able to predict the next token in a sequence. So you'll be building a language model using LSTM cells, and we'll be evaluating on your model on two fronts. One is predicting the next token in an incomplete sequence, and then completing an incomplete sequence by generating a few tokens after what has been given to you. So the prediction task, which is a single token prediction, would be 40 points, and the generation task, which is basically completing a sequence, would be another 40 points. So beginning with self-attention. So self-attention in very simple terms basically is a mechanism through which different terms of an input can focus on or pay attention to other terms in the same sequence. So if you have done embeddings, you have learned about embeddings in the previous homework as well. So when you just create embeddings for tokens, they are quite independent of each other. But if you pass them through a self-attention block, uh, the representations that you get for the tokens basically take context of other tokens as well. And the self-attention layer basically learns as to how much focus each token should put on other tokens. So self-attention is a type of attention in which the inputs, the keys, queries, and values all come from the same input. So this is slightly simpler to implement, and that's why you'll be implementing that. As for the mechanism, you basically have n tokens, each having a d-dimensional embedding. You project them into keys, queries, and values by doing matrix multiplication with certain weight matrices. The way attention works is you have to take dot product of all the queries with all the keys. That is why the dimension of the keys and queries have to be the same. We call it dq. And the value can be any other arbitrary dimension. We call that dv. So first of all, you will compute attention weights by taking dot product of each query with each key using the matrix multiplication qk transpose. At this point, each row is one token, and each row, say the ith row, has n weights, which basically tells you that how much should the ith token pay attention to any other token in the input sequence. We pass it through softmax to normalize these raw attention weights into a probability distribution. So at this stage, you have basically weights in the range of 0 to 1, which tell you that how much should each token pay attention to another token. And you take a weighted mean of the values according to these normalized weights that you have, and you use another matrix multiplication for that. So what you get finally is n tokens again, but this time the representation is of the dimension dv, and this time the representation of each token has the context of other tokens in accordance with whatever attention weights were calculated. The equations for both the forward and backward have been described in a lot of detail in the right. So you should go through the write-up and understand how this entire mechanism works. The shapes and everything are there in the table. Please pay attention to the shapes so that you can code the entire forward and backward thing. There is an auto grader to grade you on your equations, on your implementation, just like other part ones. So you'll be evaluating your um, code through a local auto grader and then submitting it to AutoLab for submission. Why self-attention is important is because it is an integral part of the transformer architecture. So there can be self-attention, there can be cross-attention. The only difference is that where the keys, queries, and values come from. In self-attention, all three of them come from the input sequence. And if you talk about cross-attention, then the keys and values come from the encoder and the queries come from the decoder. But the math inside the block remains exactly the same. So you will be using transformers in 4 part 2. So it's important that you get a taste of attention in 4 part 1 itself. Right. So do we have any doubts about the self-attention part before we jump on to the language modeling component? Okay, I'll take that as no questions. You can ping on Zoom as well, on the Zoom chat to ask questions too. Okay, so for the language modeling component, as I briefly alluded to it, language modeling is basically the task of predicting the next token given certain tokens. So, and once you can do that, you basically have the probability of each token given the previous tokens in a sequence, and that is how you can compute the probability of the entire sequence as a single unit. So there are a few concepts before starting language modeling. The first is the concept of SOS and US, which you have used in homework 1 as well as homework 3. They basically mark the starting and the ending of a sequence. So you will be prepending and appending these tokens to your training articles. Then also, how do you represent the tokens? So your training data has tokens in the form of token IDs, and you have to put them into an a higher dimensional representation, which is called embeddings. So you got a taste of embeddings in homework 3 part 2. Here as well, you will be using embeddings, but this time you don't need to use a CNN or anything. You can just use the embedding layer provided by PyTorch. Finally, once you have your embeddings and you have already appended and prepended and appended SOS and US to your sequence, you can pass the sequence through your recurrent language model, and at each time step you will get a probability distribution. And since you have the actual sequence, you can take the probability of the actual next token at each time step and multiply all of them to get the probability of the entire sequence. If instead of the raw probability you take the log of the probability and add all of them up, it is called the log likelihood of a sequence, which is basically taking the log of the probability of the sequence. So this is what you will be also using to train your model. But if you just look at this figure to the top right, you can see that at each time step, you get a probability distribution. So say at time step 2, your input is the character F, and your next character is the character O. So when you get the probability distribution at time equals to 2, then you get the probability of the character O, and that is what is highlighted in red at time step 2. And you do the same thing for all time steps, and then uh, take the log of each of the probabilities and add them up to get the log likelihood of the entire sequence. So this is how a language model helps you to do this. And about the recurrent part, you will be using LSTM cells to perform the computation at each time step. So LSTM cells are basically, you will be arranging them in like multiple layers, just like you did in homework 3 part 1. If you remember, you for your RNN classifier, you stacked up some RNN cells. So here you will be using LSTM cells, which are provided by PyTorch already. So, and you will be applying them at each time step. So this is just a pseudocode for generating the log likelihood of the entire sequence. As I said, you get the embeddings at each time step, you pass them through the RNN, and once you have the output from the linear layer, you apply a log and keep adding all the log probabilities till you reach the end of the sequence. Now you will be using the same concept to train the language model. So the objective of the language model would be to maximize the likelihood of the log likelihood of the entire training set. So once you have the log likelihood of one sequence, you can add all the log likelihoods up for the entire training set and take the negative of them to make it a minimization problem. So the loss is basically the negative log likelihood loss. And this can also be computed using the cross entropy loss function in PyTorch. So if you look at the math of the cross entropy loss function, it does exactly the same thing. So if you apply the cross entropy loss at each of the time steps, you get exactly the same loss function. So that is what we'll be using in implementation. But theoretically, it's the negative log likelihood that we are trying to minimize. As for the data set, you have been given a data set called Wikitext2. It has 579 articles. Each article has a different number of words. So your first task would be to prepend and append SOS and US to the articles. And as I said, each article has the words in the form of word IDs, which are IDs, basically indexes in the vocabulary. So you've also been given a vocabulary file, which is approximately 33,000 in size. So your training data is basically the indexes of the words in this vocabulary. You will have to code a data loader class. In the data loader class, you'll first be shuffling all the articles, and then you will be separating them into inputs and targets. So since this is a language modeling task, next token prediction, your targets are basically the inputs shifted by one time step to the right. So if your original sequence is I eat a banana and an apple every day, including today, then your target sequence would be eat a banana and an apple every day, including today. And the label for the last time step would just be the end of sequence token. Now, of course, as I said, each article has different number of words in it, and you have just concatenated all the articles together after shuffling them. So once you concatenate it, once you concatenate all the articles, you basically have a long array of tokens, right? You have to break these tokens into sequences. That is a hyperparameter. Sequence length is a hyperparameter that you have to specify. So if your sequence length is 3, as it has been depicted in this figure, your first sample would be I eat a, your second sample would be banana and an, and the corresponding labels would just be one time step shifted to the right. So for I eat a, the labels would be eat a banana. So if you do this, you'll get a lot of sequences. Each sequence will have an input and a target, and you have to batch them according to another hyperparameter batch size that you would be setting. And you have to write a loop in the data loader class, which will, at each iteration of the loop, it will just yield a tuple of inputs and targets. And both inputs and targets would have batch size number of sequences, and each sequence will have sequence length number of tokens. So this is just a high level view of what the data loader is doing, but you can read the write up to understand it better. But this should be a pretty straightforward implementation. Any doubts up till now about the data or implement the data loader? Data loader, I'm sorry. Okay. So in your language model class, you will have to implement four functions: forward, RNN step, predict, and generate. Forward and RNN step will be used while training your model, and predict and generate will consume the forward and RNN step functions, but will be used to use your model for downstream tasks. So the forward method basically takes your input sequence, the one on the token IDs, and it passes it through the entire model for each time step and generates the probabilities at each time step. So what you would do is, first of all, you will convert the token IDs to their corresponding embeddings. Then you'll iterate over time steps. At each time step, you will pass the embedding of the token at that particular time step through the RNN. You will get the final hidden state, and then you will pass it through the linear layer, which will translate that hidden state vector into a probability distribution or the logits distribution, and you will just append that to a token probabilities list. It's important to note that you do not have to perform the softmax function here, because as you have seen over multiple homeworks, the cross entropy loss takes care of doing the softmax mm, and doing the log function and calculating the softmax and doing all of that. So you just need to output the raw logits, nothing else. So the output of the forward method would be the token probabilities at each time step and the hidden states. It's up to you whether you output the last hidden state or a list of all hidden states. We do not check your hidden states, but they will be used while training your model. So it's important that you fix a convention and follow that all along. But the token probabilities have to be output at each time step from the forward method. So if you look at the second stage here, which is RNN out, comma hidden states is equal to not implemented, this is where you will be calling your layers of RNN cells or your LSTM cells in this case. So that is what the RNN step function is. It takes the embedding at a particular time step. It iterates over all the layers of our LSTM cells. It and then once it passes the embeddings through all these LSTM cells, at the final layer, you get the final hidden state, which is called embedding here. So the embedding keeps getting modified over all the RNN cells. And as an output of the RNN step function, you will be returning the final hidden state and also the modified hidden states list. So the input of the RNN step function is the list of hidden states till this particular time step, and then you output the modified hidden states list along with the final hidden state. And this was what is required to train your model. Is there any doubt up till now? Okay. So next we come to how will you use your language model for downstream tasks. So the first task is prediction. Prediction basically is that you will be given an incomplete sequence. For example, I go to the, and then you have to predict the next token. We know what the ground truth next tokens are. You will be predicting the logits for the uh, final time step, which will basically be the logits for the next token. And we'll be using those logits to evaluate how well your model is doing. If it's a really good model, then the likelihood or the logit for the actual next token will be pretty high. So that is how we'll be evaluating it. Uh, you are already given a validation set, which has the inputs and the actual targets for the prediction task. So you can use that to evaluate how well your model is doing. The training code calls the predict function that you will be implementing at each epoch. So you don't need to worry about that. You will get to know how well your model is doing on the prediction task. However, your actual score will be based on your performance on test set, which will be evaluated inside Autolab. So the starter notebook that has been given to you will calculate the logits on the test set, but you will not be given the labels. The labels are there inside Autolab, and we'll be evaluating your performance there. You have to get a, a negative log likelihood less than 5.2 to be able to clear the prediction task. So negative log likelihood, just like you had learned a few slides earlier, here we will be calculating the negative log likelihood of the final predicted token. It's important to note that the validation NLL can be zero point 0.5 or zero point 0.7 lower than what you get on the test data. So don't think that if you get a validation NLL of 5, you will clear the test cutoff as well. Make sure that you get a validation NLL of 4.5 or less than that to be able to clear the test cutoff. I say this because there is a limit of 5 submissions for this part 1. Unlike other part 1s, you do not have an unlimited number of submissions. You only have 5 submissions, so be judicious in using them. So the predict function that you will be implementing basically takes in the incomplete sequence, the token IDs of the incomplete sequence, passes it through the model. You might want to use the forward method of the model to do this. And if you remember, the forward method gives the logits at each time steps. You can just take the logits at the final time step and return them. So that is what the predict function should be doing. It was very easy to implement if you have implemented the forward method correctly. The second part is generation. Oh yeah, also there is no extra credit for getting a very low NLL. So it's either you get 40 points or you get 0 points for the prediction task as well as the generation task. It's just the cutoff that you have to beat. All right, so for generation, what you will be doing is, so for prediction, you basically predicted the likelihood of the next token. For generation, you will be predicting the likelihood of the next token, actually drawing from that distribution, feeding the token that you have drawn into the next time step, and do this iteratively for like multiple time steps. So you will be given an incomplete sequence. For example, I go to the, and you have to generate the completion of that sequence for 5 or 10 more tokens. So this is what the generation task is. So at each time step, in addition to doing the final, doing making the probability distribution, you also have to draw from the probability distribution and feed the drawn token as input to the next time step. So the expectation is if your model is really good, the generations will sound something like the training set, which is English. So it should closely resemble English. Of course, your model is not a very big model. So it won't be able to get like really good generations, but they should still not be just gibberish. Okay. How we will be evaluating generation is by feeding your generated sequences into a large language model and seeing the likelihood on that model. So a large language model is basically trained on a lot of data and has billions of parameters. Millions of parameters. That language model is expected to generate language as close to natural English as possible. So we will be accessing a large language model through the OpenAI API. and we will be passing your generated sequences through it. And if your generated sequences are good enough, you will get a lower NLL than just gibberish sequences. And we'll be measuring your perplexity. So perplexity is basically e to the power the NLL. So to be able to clear the cutoff for generation, you have to get a perplexity of less than 1400. This should be fairly easy to achieve if you've cleared the prediction task. The prediction task is more difficult than the generation task, to be honest. But the prediction task is evaluated inside Autolab, but the generation task you will be evaluating yourself. So you will be given the test set for generation, which will have incomplete sequences. You will be generating some continuation for those sequences, and then there is code in the notebook which calls the OpenAI API to calculate the perplexity. You just have to put your API key in there and then run that cell to get the perplexity number. Details on how to get the OpenAI key and how to load credits into your OpenAI account are given in the write-up. So please refer to that. But the important part is you will be getting the perplexity number from the notebook, and you will just be reporting that. We will not be evaluating all your generations in Autolab, but you will be submitting this number. But please be honest in reporting the perplexity number, because we will randomly be evaluating submissions. And if the perplexity that we calculate and that you reported differ a lot, it will count as an AIV. So please be honest in reporting the perplexity number. The pseudocode for generation is very similar to the forward method. So first of all, you uh, pass the given sequence through the forward method to generate the probability distributions at each time step. But now you have to continue generating. So first of all, you will sample a token from the last time step, and you will feed that as the input to the next time step. And you will keep doing this for in a loop. So for as many tokens as we want you to generate. So I think we are asking you to generate 10 tokens. So you will be running the loop 10 times. So to basically inside the loop, what will go is just like you did the forward method. So you have an input, which is the drawn token from the previous time step, and you have the hidden states from the previous time step. You will be feeding them both into the RNN. And once you get the RNN outputs, you will be generating the probability distribution by passing it through the linear layer. And once you have the probability distribution, you will once again sample from that and repeat this procedure. As an output of the generate function, you have to return the tokens that you have generated, not the original tokens, only the tokens that you have generated. Our code will take care of appending the original sequence to your generated sequence. Once again, please read the write-up for like more details on how this has to be implemented. All right, any doubts up till now? Okay. So to be able to clear the cutoffs in this homework, you need to implement some regularization techniques that have been described in the write-up, and the paper has also been linked. You have already explored log dropout briefly, but using an LSTM. This time you will have to implement log dropout for each time step individually. So it will be uh, a slightly different implementation, but it should be fairly similar to what you did in homework 3 part 2. There are some more of these regularization techniques that you should be implementing or you would have to implement to be able to clear the cutoffs. So general tips. So this homework part one, unlike other homework part ones, requires ablations to be able to clear the cutoff. So please start early. And as I said, and as I have said multiple times, read the write-up very carefully. It's fairly long but very detailed. So do read it. You also have to complete a homework 4 quiz, which is based on some part of homework 4 part 1 as well as homework 4 part 2. So you'll have to read both the write-ups before the early deadline of November 16. Also, as I have mentioned earlier, there needs to be a fair safety margin in your validation prediction NLL so that you don't waste an Autolab submission, and only 5 submissions are allowed on Autolab. All right, so that is all for homework 4 part 1. If you have any questions, you can ask now, or we can jump on to homework 4 part 2. Is there anything on the chat? Nope. Okay, so Dennis, maybe you can take over for part 2.
All right. Let me start. So let me share my screen. I hope you can see my screen. So yeah, I'll be talking about homework for part two. So the task in this homework is to implement an attention-based system to solve a sequence-to-sequence problem. So in this homework, what you'll be doing is the model will ingest speech or MFCCs and using the listener, and we shall be using the attender and the speller before decoding out what the person was saying. So here, the use of the attender is to provide context to the speller as it tries to decode what the speaker was saying. So for instance, in this example, we have speech going in, and yeah, the transcription of that speech is the quick brown fox, and then continues to complete the sentence. So the encoder in this homework will be a transformer encoder. So here, as explained in lecture 19, there was an exclusive explanation of how the encoder works, whereby we take in the inputs, we have input embedding, use the positional encoding because the transformer does not use recurrence. We want to tell the position of each of the tokens. So we use positional encoding to assist with that. Then we pass it to the multi-head attention, which was clearly explained in lecture 19. After applying multi-head attention, we also have a we also have a recurring. So we have a connection between the input and the output of the multi-head attention. We apply add and norm, then we pass that to the feed-forward neural network before we again apply add and norm. Then this output is what will go to our attention layer. So as the explanation goes here on the slide, we have the encoder derives feature vectors from the input sequence of the speech vectors. So that's the purpose of our encoder here. So the input speech feature vectors have strong structural continuity with adjacent vectors as well as long-term contextual dependencies. So you may find that in this task, it's not only the neighboring like MFCCs of a given MFCs that's under consideration that are important when we're decoding. I find that there are very long-term dependencies that need to be considered. So that's the role that will be played by the attention layer, attention block. So in this homework, we also have the decoder. So the decoder is a language model that I've just explained. So the language model has extensively been covered in homework 4P1. So having implemented it in homework 4P1, there are not that many changes that need to be made for it to work as a decoder for this case. So it's highly recommended for you to implement homework 4P1 before starting homework 4P2 because that will enable you to have a working decoder before you can embark on the task in homework 4P2, which is quite complex. So in addition, we have the attention block. So attention block, what it does is when you're decoding, we want to consider some MFCCs that are important to the particular step that you are at. So this may not be the immediately neighboring terms, MFCCs like we had in homework 1 part 2, but so that what the attention block does is we use the keys, queries, and values whereby the query will come from the decoder and the keys and values will come from the encoder that we just saw. So what attention does, it calculates the amount of attention that the model is supposed to pay to particular features while decoding at every step. So here we are. There's a question: why is attention important? So it relates to what we saw in homework 1 part 2, whereby we had context, but in our homework 1 part 2, the context was fixed in that we only considered the neighboring MFCCs when decoding. So here, as you can see, we have this is a typical attention diagram that you are likely to get, whereby you have the speech the MFCC at step 0 has a high correlation or attention to this transcript at step 0, But in some circumstances, it may be that may not be a perfect diagonal. So in some cases, you might find that the last word pays attention to the first one. So that's why in some circumstances, you may find that the attention block is not perfectly diagonal. Then, so here we continue to show examples of this. So here we're asking the question, will the attention diagonal always be diagonal? No. So you'll find in some circumstances, for instance here, that it's not perfectly diagonal. There are some misalignments, but this just shows that when it's decoding at this particular time step, it's not only, it's paying attention to some other time step in the speech. So this as well shows further examples. So when you should expect to see such attention diagrams when you complete the homework. So for the baseline architecture for this homework, we shall be using the listen, attend, and spell. But for this particular one, we shall be replacing the listener in this paper with our transformer encoder, which was explained in this paper of attention is all you need. And it was as well explained in lecture 19, which you can go back and review. You can also read the paper for further understanding of what to do. So in the starter notebook, as I'll go through it later, we have the dataset class, we have the data loader, the model. So you'll have to implement the baseline model, so the encoder in this model will use a CNN and a transformer encoder. The attention mechanism, we shall use multi-head attention. There's a thorough explanation in the write-up, as well as guidelines in the notebook to help guide you as you code this part. The decoder, as we had explained earlier, this is what was used for homework 4P1. So you're encouraged to complete 4P1 before you can embark on 4P2. Training. So for training, you'll have to train. This homework is quite hectic, so you'll have to train for much longer than we usually do for part twos, and you have to be very patient with your model as it trains, because it takes quite some time. As well as the inference stage, which should be follow what we've done in the past. So things that we'd like you to keep in mind: use mixed precision training. I think some of you have implemented it in the past, but for those that haven't, I think you need to implement it, because it really matters in this homework, as without it, the model will take significantly longer to train. So here, as you know, since we're decoding speech, so we're decoding real words, there are two ways of approaching this. You could use word-based or character-based, but here we encourage you to use character-based. The reason is when you're using character-based, you're able to decode rare words which may not have existed in the word vocabulary. So that's one of the advantages, but it also has some downsides in that it takes longer. It takes longer to train. So here we have processing the transcript. So use the vocab map, which is provided in the starter notebook for index to character, and vice versa, as we shall see later as I explain the notebook. Then use built-in PyTorch libraries for packed sequence and back-padded sequence, as I'll show later. So things to consider while you do this homework. So whereas in your transformer encoder, you could have used self-attention, single-headed attention, we encourage you to use multi-head attention, because it's given that it will produce much better results. Then when you're doing inference, you can use one of these three, whereby you can use greedy search, random search, or beam search. So you can test out all these three as an ablation in your groups to see which one works best. Then we also have to use teacher forcing, I think, which was explained in one of the lectures, I think lecture 18. So we have to use teacher forcing because in some circumstances, the model may predict something that's significantly longer, which may not enable calculation of the loss. So we use teacher forcing, which helps us in calculation of the loss and helps to improve the model. For further information about teacher forcing, you can look at this link, which is attached to the slides. Then we shall be using Levenstein distance to evaluate your predictions. and make sure that when you're decoding, you remove the EOS and the SOS, as these were not included in the actual labels that will be used to evaluate your outputs. So you have to attempt to use several weight initialization techniques, as we have seen in the past. You may also need to use some regularization, because if you build a very huge model, you have to regularize it to prevent overfitting. Then, in addition, you can use data augmentation techniques like time and frequency masking. For optimizers, would advise that you use Adam or Adam W with weight decay. In terms of learning rates, use 1 exponent negative 4. We have attempted to use higher learning rates, but these have not resulted in a good performance. Usually the model ends up diverging. So we advise that you use a maximum of 1 exponent negative 4 as your learning rate. Then, so in some cases, it may be useful to pre-train your listener, as this will help the model to train faster. Then you can reuse, as you've seen earlier, you can reuse the decoder that you trained in homework for P1. Are there any questions at this point before I proceed to the notebook? All right, so if there are no questions, I'll proceed to review this is the starter notebook that you're given. Here we attach links to the competition and the data set, plus the two papers that we shall reference in this homework. So these are the usual lines that we use. So we shall have to install some packages, the Levenstein distance, torch summary, 1db, and the usual packages that we use. Here we shall go ahead and import them and check whether we have access to the GPUs. This is the config file which you can use to log your configurations for your model. So in terms of the dataset, we've provided several options. So we have the train clean 100 and train clean 360, but you can as well combine the two and form the train clean 460. And in the dataset class, we have provided for your provision of combining these two classes. So here we have a Kaggle. That's the usual stuff that we have to download the dataset. So then we shall move on to the vocab. So in vocab, here we have all the characters that you'll have to encounter during training of your model. So we have the PAD token, the SOS token, EOS token. I know that from the lectures we've covered the purpose of these. That the SOS token indicates the start of the sequence, which shows the start of the sentence, and the EOS shows where the sentence ends. The rest are the letters of the English alphabet, which you shall be using in this case. So we provide for you a method to map from this vocabulary to integers and back. So that is provided in this cell. So then we can move on to the speech dataset class. So here we provide a memory efficient implementation of the dataset class, because unlike previous homeworks, this homework has significantly more data. For example, so if you're to load the train 460, you need to use the memory efficient implementation, otherwise it would not fit in your RAM. So here we provide provisions. So here you can select the partition using this parameter. So you can change it to train clean 100, 360 or 460, but we'd encourage you to use either 360 or 460, because we found that the train clean 100 didn't converge. So we have provisions for you to fill in, and guidelines as you fill in this code. So you'll have to implement the init class, the length, as you've been doing in the previous homeworks, of the get item and the collect function. I think you've encountered this before as well. So this should be easy for you to implement. Then we have the speech dataset test. So this is for loading the test dataset as well. So there are a few to-dos in this class as well, but they should be easy once you've implemented the one before. We also provide these. We provide the data loader for this homework as well. So you shouldn't have to worry about that. Then you can test whether your data loader is working using this cell. So if you're using either the train clean 100 or 360 or 460, you should be able to see output that's similar to this. It may vary depending on the dataset that you decide to use. Then we provide a verification, but this is for the train clean 100 and provide you with the output that you should get. So if your output doesn't match the output that's given in this markdown cell, you should try to check for errors that you may have had in your code. So then now we're going to move on to the model. So as I had said earlier, we are attempting to use the listener tenant spelled model, but in this case, we're going to replace the listener that they used in the original paper with a transformer encoder. So here we provide a class permit block, which is used to change switch the second and third indices of the data. Then we also provide a function to plot your attention to get the diagrams that I shown earlier in the slides. We provide a method to save your model and to load a model for you to be able to continue. We also provide a class that checks the amount of time that the model takes to train per epoch. So this should be useful for you to check how long your model is taking to train per epoch. So as I'd shown earlier in the image of the transformer encoder, you need positional encoding. So positional encoding is important because given that the transformer does not use recurrence, it has no sense of location. So we use positional encoding to give it a sense of location for each of the tokens that is used. So you'll be able to implement positional encoding. We provide some pseudocode in the write-up, which should help you to implement it easily. Then from there, we can move on to the transformer encoder. So here we use the same kind of attention that was explained. So we use keys, queries, and values. So we provide all the blocks that may be necessary. You just have to fill in the code. So here, for the attention in the transformer encoder, I think you're free to use multi-head attention provided by PyTorch, given that you already coded the attention in homework 4P1. So you can implement each of these blocks, and we provide all these methods to help you with this. So from there, you can then print your model and check it out. That should be for you to verify that your implementation is right. Then we provide the transformer class. So the transformer listener combines everything that we have implemented before. That is the transformer encoder, and you can use convolution, 1D convolution layers for your embeddings. Then we have positional encoding, which we have explained the purpose, and then the transformer encoder, which we implemented earlier. So here, as you will see in the paper itself, in the attention so you need paper, they have several attention transformer blocks. So the transformer blocks will be part of the ablations that you'll have to do. How many transformer blocks should you use for your particular implementation? That can vary. So we encourage you to do ablations and see what works best. So from there, we have the forward method as we've had in the previous homeworks. Then now we can move on to the attention block of the homework. So here we have we're going to use dot product attention, which was explained in the attention is all you need, and which you actually implemented which you'll have to implement in homework for P1, as shown earlier. So just to make you aware that there are all these kinds of attention, but for this particular homework, we shall be focusing on dot product attention. And then we encourage you to use multi-head attention, which is a form of which is an extension of the scale.product attention that was explained in class. So I think in lecture 19 we went into depth of why you need multi-head attention, because the model may need to consider several aspects as it decodes. So we encourage you to try out multi-head attention, or so you can start with dot product attention and then move on to multi-head attention if the dot product attention doesn't work for you. So we provide the pseudocode in these blocks, so it should be a bit easier for you to implement. So in the attention class, we provide three methods. That is the init, set key, and set key value. So this is where you will calculate the key and value, then you will compute the context using this compute context method. So in the write-up, we provide the pseudocode, and which is provided in this markdown cell as well. So you should be able to follow this to have your implementation. Then we can move on to the speller. So the speller, as we had explained earlier, the speller is quite similar to what you'll have implemented for P1. So, but the speller will be making use of the attention. So the speller and the attend block are connected. So you'll be making use of the attention. That's why you will pass it. Then there are maximum time steps. So if you're given the label, you'll be able to determine the maximum times, because your transcription. So what you decode should match the label in terms of length for you to be able to calculate the loss. But at test time, when you don't have the label, you have to use this parameter, which is the maximum time steps, which determines how long you're going to decode. And in the write-up, we recommend that you set this value to around 550, because we've seen that to work in the past. So the rest of the parameters should be filled in as we've done for homework for P1. We have the LSTM step where you'll be using LSTM cells to implement. So to implement this, and all of this is provided in the write-up for this homework. We have the CDN, which is the character distribution network. So this is used to convert. So this is used to convert to the space of the characters, that is the vocabulary size. So here you'll use a couple of linear layers, which will enable you to convert to the vocabulary dimension. So we've provided pseudocode in the write-up, which can help you implement this as well. Then you'll make use of all the other methods that we've implemented prior in the forward function, but it is quite similar to what was done in the 4P1 exercise, in the language model in 4P1. So the ASR model, so this combines everything, the listener, the attend, and spell, and so to put together the model that you'll be training. So here you can fill in the parameters for the model. Then here we set the optimizer, the loss function, the scaler, and the scheduler that you'll be using to train the model, as we have done in the past. Then we provide you with a function that will be used to convert the integers to characters. So Levenstein distance is calculated on characters. So you'll need a function that will convert the integers that the model produces back to characters for you to calculate the Levenstein distance. So we provide this function that will enable you to do that. We also provide this calculate edit distance, which is like calculate the Levenstein distance function. So you don't need to worry about this, because it will be provided. It's provided in the write-up. Then we provide the train function as well, train and validation functions. Then in this cell, you can initialize your 1DB runs so that you're able to track your model. We provide here in this cell, we provide the plot attention function. So this will enable you to check how well your model is doing, whether you're getting the diagonal or not. So the diagonal tells you if your model starts forming the diagonal, then you're able to see that it's working well. Then in this cell, you can go on to train the model for the number of steps that you set in your config file. And that should be it. Are there any questions? Or if there are no questions, we shall share both the slides for the 4P1 and the 4P2 bootcamp. Thank you.